All right, get your lightning bolt emojis ready, folks. It's time to talk about energy. When I first took an environmental science class, I didn't quite get why energy got its own section. Because in a lot of ways, energy feels so detached from the environment. I mean, in order to produce and move energy, we dig deep into the ground for fuel. We burn that fuel to create electricity, and we clear trees to make room for power lines. It all seemed in opposition to the environment. And in a lot of ways, well, it is. Most energy production is entirely extractive. The extraction and the resulting pollution from most energy sources has an immense impact on the environment. And that's why we've got to talk about energy in the context of environmental science. But before we go too far, let's talk about what energy actually is. At its most basic, energy is the ability to do work. So flowing water has energy, and it can carry objects along with it. Heat is a form of energy, and it can make molecules move faster. Generally, energy gets discussed as potential or kinetic energy. Potential energy is stored energy, like the water behind a dam, or energy bound up in the hydrocarbon molecules within a lump of coal. Kinetic energy is the energy of motion, like that of flowing water or superheated steam. But energy, well, it's not much use on its own until it's harnessed to do stuff. And both potential and kinetic energy can be harnessed to do work. And when we spend an amount of energy on work over a period of time, that's power. Congrats, now you know what those numbers on your light bulbs mean. But how do we turn a lump of coal or underground heat or flowing water into that kind of energy that makes a light bulb switch work? Or the more specific question, how do we harness that potential or kinetic energy and turn it into a flow of electrons? Now, we all learned in physics class that energy cannot be created or destroyed, and that's true. But in the context of environmental science, when we say generating energy, we're talking about the conversion of various types of existing energy out in the world into electrical energy that we can move and actually use. And most of the time in power plants, from coal to gas to hydro, we create this electron parade by rotating coils of wire around really big magnets. The magnetic field moves the electrons within the wire, generating electrical energy. This device is called an electromagnetic generator, and it transforms mechanical energy into electrical energy. To keep the generator spinning, we use a turbine. It's basically a big, fancy-looking fan thing. And that is kept rotating by our energy source, which could be flowing water or wind, but is often steam coming off of a heated liquid. This chart summarizes the primary ways in which we generate electrical energy. We've got burning fossil fuels, capturing wind and flowing water, or tapping into the intense heat under the ground. Even splitting atoms, like in a nuclear power plant, ultimately generates energy in the same way. Uranium atoms are split to generate enough heat to boil water that makes steam to spin a turbine to rotate the generator to make energy. Of course, off in the corner there is the primary way we generate energy without an electromagnetic generator: solar. Photovoltaics convert light energy from the sun into electrical energy without the need for bulky turbines or generators. This chart also highlights which sources are renewable, meaning we could never run out, no matter how much energy we make from those sources. And the little flame emoji, well, that means those sources generate electrical energy and can be used for heating. It's a term called cogeneration. And there's one major fossil fuel missing from this chart: oil. Crude petroleum isn't really used to create electrical energy anymore. While oil-fired power plants do exist, in the US they only make up 3% of energy generation. But oil is still a major form of energy and carbon emissions, just mainly in transportation and in making plastics, which we will talk about shortly. Okay, so we have all these ways of generating energy. Why does an environmental scientist or just the average person need to know about all these? Well, as we talked about in the climate and air episodes, each of these forms of power generation carry their own risks for making a big mess of the planet, and some far, far more than others. So for each of these energy sources, we need to know how it works and what are the pros and cons. Knowing more about each of these can help us transition to a more sustainable energy production in the future. Or now, let's start with the most common way of generating energy today: burning fossil fuels, mainly coal or gas. Now, when these combust, they release huge amounts of energy. But where does all that energy come from? And what even are fossil fuels? Well, like many things on the planet, it all starts with the sun. Millions of years ago, plants loved sunlight just like they do today. All plants, from marine phytoplankton to savanna grasses to those massive fern palm things that flourished during the Carboniferous period, rely on sunlight for photosynthesis. and through photosynthesis, that light energy from the sun is stored in the plant's bodies. Generally, we can track that energy as it moves through the food web from producer to consumer or to a decomposer. But during the Carboniferous period, when most of our fossil fuels were created, there was such an abundance of plant life that when those plants died, not all of them were eaten or decomposed. Instead, those plants and all of their stored energy from the sun got buried under layer after layer of sediment. And after millions of years of heat and pressure from the weight of all that earth, the organic materials in those plants became the hydrocarbon fossil fuels that we use today: coal, oil, and gas. The difference in the formation of those three is mostly a matter of how much heat and pressure they were exposed to during formation. And once people figured out there was eons worth of stored energy underground, they developed special mining techniques to get it out. So for coal, if the coal seam or layer of coal isn't too deep underground, a technique called surface mining will be used. The soil and rock above the coal, called, unironically, the overburden, gets removed by massive surface miners and dump trucks, either by burrowing down into the ground or grinding away the surface layer, which, as you can imagine, isn't that great for whatever ecosystem was there before. And wherever we dump all that overburden also has serious impacts on the ecosystem. Another form of surface mining is called mountaintop removal valley fill. If there's a suspected coal seam inside of a mountain, they'll literally blow up the mountaintop or ridge in order to start a surface mine and then dump the overburden in a nearby valley. If that wasn't bad enough, the process of surface mining also releases large amounts of carbon dioxide, which, as you know from the last episode, is a powerful greenhouse gas involved in climate change. To get at the really buried stuff, miners turn to subsurface mining. In this method, large shafts and tunnels are dug into the ground. Humans and large machines travel down those tunnels to extract the coal. This type of mining is more expensive, and the process is more dangerous to humans than surface mining. Surface and subsurface mining can radically alter the topography of the Earth, resulting in higher rates of erosion as well as habitat loss, and can cause severe water pollution issues. As water flows through these mines, it runs across coal waste, picking up sulfur and creating sulfuric acid. And this acidic water leaches out metals, which can be toxic. Once mined, the coal is transported, often by train, to coal-fired power plants. At these facilities, the coal is burned and the heat generated is used to boil water to make steam, to turn the turbine, and to spin the generator to produce electrical energy. But as the coal burns, it releases pollutants into the air that harm both the environment and human health. In the air episode, we talked a great deal about the different types of pollutants emitted during this combustion process, and none of them were good for us, which is part of why the number of coal plants, especially in the United States, is going down. Not only do they produce massive amounts of carbon dioxide emissions and air pollutants, but these days coal mining and coal-fired power plants have a hard time competing economically with other cheaper forms of energy production. Oh, and one last thing about coal. When coal is burned for energy, we're left with all these extra particles and residue called coal ash. To keep the coal ash from getting into the atmosphere, coal-fired power plants often have these kind of landfill ponds where the ash gets dumped. But a large hazard like a flash flood or a dam bursting can easily flood those ponds, releasing toxic coal ash sludge everywhere. And this happened in 2008 in Tennessee, when billions of gallons of coal ash slurry were flooded onto the surrounding areas. Next, gas, or what many people call natural gas, but should really be called fossil gas, because there's like a whole history about people calling things supposedly natural, which we can talk about another time. Now, like coal, gas comes out of the ground ready to use, but gas releases less air pollution than coal when burned, but not zero air pollution. Extraction and use still cause a lot of environmental problems. Gas is mainly methane, and a lot of it is located in pockets that are sandwiched between layers of rock. This is relatively easy to drill down and extract. Way easier by comparison to building a massive surface mine that relies on heavy machinery. But there are also massive stores of gas located in the pores of underground rock formations. To extract this gas, a process called hydraulic fracturing, or fracking, was developed. In fracking, holes are drilled deep underground into these rock formations, and a mix of pressurized water and sand and chemicals is then injected into the hole to crack open the rock and release the trapped gas. Now, fracking opened up access to a lot of gas that had previously been too difficult or expensive to extract, making gas a much more common and cost-competitive energy source for generating energy in the last few decades. While burning gas releases less air pollution and greenhouse gases than coal when it's burned, it's still a big source of emissions. And not only that, the fracking process can accidentally leak methane either directly into the atmosphere or into the groundwater below. In 2015, a gas well in Aliso Canyon leaked an estimated 97,100 tons of methane into the atmosphere. And once methane's there, it's a very powerful greenhouse gas and a major contributor to climate change on its own. When methane or fracking liquids seep into the groundwater below, it can be dangerous to living organisms, including humans, who may use that groundwater as a drinking source. Okay, I've had enough of combustion. Let's talk about other forms of energy generation, like nuclear fission. Fission releases energy by the splitting of atoms, not combustion, so one powerful benefit of nuclear energy is it does not release air pollutants or greenhouse gases as it generates energy. Fossil fuels are burned during the construction of the power plant, during the mining and transportation of nuclear fuel, but once a reactor is up and running, there's basically no emissions. The fuel for a nuclear power plant is uranium. Splitting open this radioactive nucleus by bombarding it with neutrons makes new radioactive particles and lots of energy. Once the fission chain reaction starts, it wants to keep going, so it has to be carefully monitored and controlled so that it doesn't produce too much heat. The heat from fission, like in other power plants, is used to boil water and make steam and spin a turbine to generate energy. The temperature of the nuclear reactor itself must also be controlled. If it's not regulated and constantly cooled down, then it could overheat and cause a nuclear meltdown. During a nuclear meltdown, something goes wrong with the circulating water system that's used to regulate the temperature of the reactor. And if this water circulation system fails, the nuclear reactor overheats, melting the protective containment building itself and releasing radioactive material. The world has seen 3 big nuclear meltdown accidents in the past. The largest US nuclear accident was a partial meltdown at 3 Mile Island. It didn't result in any deaths, but it caused panic and concern about whether or not to build more nuclear power plants. Another accident was Chernobyl, where thousands of lives were lost after radiation escaped into the air because of a meltdown. Finally, in Fukushima, Japan, a meltdown contaminated the area, but was contained enough to minimize the human health effects. Now, all these meltdowns are being studied today so we can better understand the effects of radiation on humans and the environment. These accidents, while they're pretty scary, are rare. A more pressing concern is what to do with spent nuclear fuel. Uranium stays radioactive for a very long time, so used fuel rods must be stored safely somewhere for a very long time until that radioactivity naturally decays. Right now, we do not have any long-term storage plans for such high-level nuclear waste. Now, currently, most is stored temporarily on-site at nuclear power plants in large pools of water in specialized buildings. How to permanently handle such waste is a very real concern when it comes to generating energy from nuclear fission, especially because countries like the United States and Australia have kind of a bad habit of dumping this waste on indigenous lands. So while there are very real environmental benefits to using nuclear energy, not many emissions, there are potentially negative consequences, particularly in the context of environmental justice. Now we've covered all the major non-renewable forms of energy generation. Basically, for coal, gas, and uranium, we consume these resources at a rate that's way higher than they can be naturally replenished. While it may take millions of years for coal to form, we can mine it and burn it within days. This type of energy use is unsustainable, and as we've talked about, can have intense environmental impacts. But, shocker, there are ways to generate energy using renewable resources like wind, water, the heat in the earth, and sunlight. With wind energy, wind spins a turbine, a very big turbine, which rotates a generator to produce energy. Thanks to the sun and Earth's rotation, wind is renewable. We aren't running out of it ever. And aside from the initial production and construction of a wind turbine, no emissions are produced during energy generation. Wind turbines, as beautiful as they are not without their drawbacks. From an ecological perspective, the turbines do pose a risk to birds and bats, and the construction of a field of wind turbines does result in some habitat loss. This can be mitigated somewhat with careful site selection, and is just one of many ways that environmental scientists can be involved with energy production. And it is worth noting that the emissions from extracting and burning non-renewable sources like coal and gas do a lot more damage to birds and bats than, entire ecosystems than a wind farm ever will. The main drawbacks of wind energy are location. Not everywhere has wind, and intermittency. Places that are windy, they aren't windy all the time. Without careful planning, the electricity production of a wind turbine may not match the demand of the consumers. Intermittency is the biggest hurdle for energy generation like wind and solar, but well-designed and managed grids with additional forms of energy storage can solve this problem. Okay, on to hydropower. Instead of using the motion of wind, a hydroelectric dam uses the motion of flowing water to generate energy. A dam controls the flow of water in a river and creates a reservoir. The water held in this reservoir has potential energy, and the more water, the larger the difference in height between the reservoir and water downstream, well, the more potential energy. When that water is released and channeled through the dam, that potential energy is converted to kinetic energy and can spin the turbine and generator. But people have been producing energy this way for a really long time, and dams do have a lot of benefits. That reservoir can be used for recreational activities, commercial fishing, or agricultural irrigation. But dams are highly location specific, need the right amount of water and topography, and constructing a dam is super expensive. Plus, there is a significant disruption of the river ecology. And while long considered an emissions-free source of energy, hydroelectric dams can have a lot of emissions. Not only is the construction extremely carbon emitting because of the sheer amount of concrete used in building a hydroelectric dam, but also creating that reservoir, it ends up flooding a lot of land. That organic material previously on the land can't survive underwater, it dies, starts to decompose, and that decomposition releases greenhouse gases. This can be mitigated, and there are hydroelectric dams with reservoirs that serve as carbon sinks. This means that more life grows in them that draws down carbon than decomposing emits. This needs to be taken into account when the dam and reservoir are constructed. And now for our last turbine and generator energy source, geothermal. Geothermal uses the heat from deep within the earth to generate steam to spin the turbine and generator. Now, water, or another liquid, travels deep underground, it's heated, and then heads back to the surface where it's pressurized, heating it up further, releasing steam to turn the turbine, and then the now cooled water heads back underground to do it all over again. The process of geothermal energy generation doesn't release emissions or pollutants, with the exception of the initial construction, and sometimes the accidental release of hydrogen sulfide from groundwater into the atmosphere. However, geothermal plants work where the heat from the Earth's inner layers are close to the surface, which limits it to areas with lots of volcanic activity or near the edges of tectonic plates. And a lot of the best locations for geothermal, well, they're already in use. The country of Iceland is the poster child for renewable energy. Nearly all of their electrical energy comes from renewable sources. In 2016, about 27% from geothermal and the rest from hydropower. And last, but certainly not least, we have solar energy. Solar energy production, unlike everything else we've talked about, doesn't use an electromagnetic generator. Instead, when light hits the semiconductors within the photovoltaic cells, the photons in the sun's energy knock electrons free and form an electron flow. Solar panels have way fewer moving parts and are much easier and cheaper to construct than any of the other forms of energy generation that we've talked about. Plus, their only location dependency is that they need to see the sun. Sure, some places like a desert in the US Southwest will be more efficient than the cloudy forests of British Columbia, but solar panels will produce at least some energy in any place that the sun hits. Solar panels have gotten increasingly less expensive in the last few years. In many places, solar energy generation is cheaper than coal and gas, and it looks like it'll only get cheaper in the future. But like wind, the sun is an intermittent energy source. Solar panels won't generate energy at night. And while energy generation from solar doesn't release any emissions, solar panels do rely on really specific materials to function, and many of those need to be mined, which can create emissions and pollution all on its own. And those mines are often very dangerous for the people working in them. Okay, let's take a minute to catch our breath, because covering all that energy took a lot of energy. Depending on where you live, the percentage of energy from each of these sources can be pretty different. And it's changing year to year as renewable sources get cheaper and the global demand to reduce greenhouse gases rises. But we've got one last fossil fuel to talk about, oil. We generally don't use oil to generate electrical energy these days. Rather, it's primarily used as a transportation fuel and to make plastics. Oil, like fossil gas, is found in underground pockets, trapped in rock and accessible by drilling. And once this crude petroleum is pumped from the ground, it's sent to a refinery where it's separated out into different fuels, such as gasoline, diesel, or aviation fuel, as well as products like asphalt and lubricants. And surprising no one, like the other fossil fuels, the combustion of oil results in air pollution and carbon dioxide emissions. And it's a lot of emissions, because at least right now, nearly every car and train and plane that you've ever seen, and the millions that you haven't, run on some form of oil, pumping out carbon dioxide for every mile or kilometer, depending on where you're from. One of the unique and deeply unfortunate environmental consequences of our use of oil is the frequency of oil spills during transport. Whether it's a pipeline leak or an oil spill from a tanker in the ocean, oil can cause lots of damage to both terrestrial and aquatic habitats. The largest oil spill in the US was in 2010 when BP's Deepwater Horizon exploded in the Gulf of Mexico, resulting in millions of gallons of oil contaminating coastal and marine ecosystems. Now, if we look at global primary energy production, fossil fuels have and continue to dominate despite the abundance of far more sustainable energy production options. And changing that is going to require massive global buy-in and a reframing of what energy use looks like. The energy generation and transmission infrastructure that we've constructed since the days of Edison, Westinghouse, and Tesla are in a way the largest and most complex machine that humans have ever built. I mean, it powers every facet of modern society, and shifting a process 200 years in the making isn't going to be easy. But for the health of our planet's ecosystems and the people who rely on this place, we have to. Thanks for joining us on this tour through the essentials of environmental science. Remember, we've got more videos in this series on things like climate change, air pollution, soil, and aquatic ecosystems, so be sure to check out those videos too. And we hope to bring you more of these in the future, so let us know what you thought of the series down in the comments. And in the meantime, there's dozens of other videos about climate change and the environment waiting for you on Hot Mess.